Okay, the recording has started. So let's begin. Good evening, everyone. My name is Chandan Kumar Gupta. I am a Prime Minister Research Fellow in Department of Mathematics, IIT Patna. I am your NPTEL-PMRF Teaching Assistant for the course Probability and Statistics. This course is offered by Professor Somesh Kumar. He is a faculty in IIT Kharagpur. This is a 12-week course, and we are in the third week live session of this 12-week course. Okay. So in the previous 2 weeks, if anyone have any doubts or want to ask any question, you are welcome. Okay. At any point of time, you may interrupt me in between and ask anything which you want to know. Okay. So in the first 2 weeks, we will discuss about algebra of sets. Then we will discuss about the basic definitions of probability actually. In which we have discussed three definitions like classical, which is also called mathematical definition of probability, statistical definition or empirical definition of probability, and the axiomatic definition of probability. Besides this, we have discussed about random variables. And before the random variables, we have also discussed like the basic probability, the conditional probability, and the most important Bayes theorem, which is actually a kind of conditional probability. We have also discussed about total law of probability. And multiplication rule. Then we have also solved one question with the help of De Morgan's law, with the use of De Morgan's law. So there are so many topics are there like ring field, sigma field, etc. So in above these topics, if you people have any doubts, you may ask. Okay. And now in week 3, we will discuss about moments. Okay. How the moments is defined, what are the meaning of moments, and how can we use these moments to evaluate some other statistical characteristics of the data or obviously data. Okay, so let's discuss about moments. Okay. Discuss some, we will just take some snapshot and then we will solve some numericals based on those topics. Okay. So the first thing is moments. Okay. So moments are defined as you may say expected value. Let me start with the basic one. The expected value of X, which is also known as the mean value, the expected value, the average value. Okay, this is the first moment actually. So the expected value of X is defined as the summation X, probability that X is equal to X, and the summation is taken over the value X. Okay. So here you may find that actually we have we have taken the average value. Okay, but we assign weight as probability. We assign probability as a weight. Okay, so this is the expected value of X, which is also known as average value, mean value. Okay, and in discrete case, in discrete scenario, when we are dealing with discrete random variable, when we are dealing with discrete random variable, then this is the formula. Okay. But in case when we are dealing with the continuous random variable, okay, then the formula is like this. Okay. So this is defined as the expected value of x, which is the first moment. Okay. This is the case for continuous variable, continuous random variable. Okay. So this is the first moment actually. Again, we have the second moment as well. Then we have the third moment and so on. So in general, let's define the kth moment. The kth moment is defined as the summation x to the power k probability that x equal to x. The summation is taken over x for discrete case or for continuous case x to the power k fx dx, the integral over x. Okay, this is the kth order moment. This is the kth order moment. Okay, when we take the value 1, 2, 3, and so on, then we will calculate the kth moment. Also, there is one more thing actually. This can be also represented by mu k dash actually. Okay, so we have two moments. Okay, we have two moments, and this one is known as non-central moment. Okay, then also we have a central moment, the similar one. Okay, it is defined as mu k, which is expected value of x minus mu k. Okay, that is we shift the parameter, we shift the location. Okay, we shift the location, that is minus or plus mu. Here the mu is the average value or the mean value. Okay, so it is again defined as the similar way, summation x minus mu. Just replace x with x minus mu and nothing more. Probability that x equal to x, or you have to take integral x minus mu to the power k PDF of s. Okay, so this is known as the central moment. Just terminologies. The central moment. Central moment is defined. Now, can anybody confirm? Is my screen visible now?
No, are you writing something? Have you
No,
shared
no.
your writings?
I'm just sharing my screen now.
Oh, yeah, we are
It
right.
is
Yeah, now yes, it is coming now.
Now it is visible. Okay, okay.
Yeah.
Thank you. Okay. So we have discussed in the previous week about these topics. Okay. And in week 3, we will discuss moments. Okay. So moments are defined as the values of the random variable multiplied by the probability itself. Okay, so it is taken as sum for the discrete case, and we take integral x into fx dx for the continuous random variable case. Okay, then we have two kinds of moments actually. The one is non-central moment and then other is central moment. The non-central moment is defined as like expected value of x to the power k, which is defined as x to the power k times probability value and taken the summation over the value x for the discrete case, and for the continuous case we replace the summation sign with the integral one. And in the central moment case, uh, the same like the we use the same concept, but we shift the origin from 0 to the mu, that is the mean value. So the expected value of x minus mu to the power k equals summation x minus mu to the power k into probability value. And for the continuous case, we take integral sign. So these are the non-central and central moment. Now we have a relationship between the non-central and central moments. So there is like the first non-central moment. The first central moment actually is 0, and this case always holds. Is it feasible? No, I'm writing actually. Can anyone confirm? Because I'm not able to like see the messages actually.
Yes, you are visible,
Visible? No? Okay, thank you.
audible.
Okay, and my screen is visible. No? Like I'm
Yes,
writing
yes,
something.
yes, yes, yes.
Okay, thank you, thank you. So like the relationship, there is relationship between the central and non-central moment actually. And the first central moment is always 0 because the sum of deviation from mean is always 0. Okay. The second moment is like the second central moment is related with the second non-central moment in such a way that mu2 equal to mu2 dash minus mu1 dash square. And this second non-central moment we will discuss in like later classes is called variance actually. In this class even as well. Okay. And then we have the third order moment as well. The third order moment is like mu3 dash minus 3 times of mu2 dash and mu1 dash and plus twice of mu1 dash whole cube. And also, actually, we have learned the first four, like the first four relationship between the central and non-central moments. So the mu4 is mu4 dash minus 4 times of mu3 dash mu1 dash plus 6 times of mu2 dash and mu1 dash square minus 3 times of mu1 dash to the power 4. So when we are able to calculate the non-central moment, then with the help of those non-central moment, we can calculate the central moment via these relationships. There's a general relationship even also exists like mu n, nth order, summation I from 0 to n, n choose I, mu n minus I prime or dash minus of mu1 prime to the power I. So this is the general formula for the relationship between the non-central and central moment. And also, actually, we have something like we are easily calculate the non-central moment. Okay, so we are easily calculate the non-central moment with the help of the moment generating function even. Okay, so there we can use this relationship. Now the next topic is expect. There are some properties like expected value of x. As we know, the moment, the first order moment, the expected value of ax is a times expected value of x. Okay, the expected value of x plus b is equal to expected value of x plus b. So these are like depend. That is the expectation depends upon change of origin and change of scale. Actually, the when we multiply or divide some when we multiply or divide some scalar with the random variable, then we like change the scale. And when we add or subtract in like a variable, then it is called change of origin. We shifted the origin from plus or minus time minus values. So the expected value depends on the change of scale as well as, sorry, depends on change of scale as well as change of origin. On the other hand, the variance, the second order non-central moment, variance of ax plus b, this is actually a square times of variance of x. And variance of b, that is b is a constant, and the variance of constant is nothing but 0. So that comes out, that vanishes actually. So here the variability only depends or only affect with the change of scale. Okay. Now we have skewness and kurtosis. So skewness means what? Like when we measure the symmetricity of the distribution, then in that case we are talking about skewness. So that means, excuse me, I think someone has forgotten to mute himself or herself. Please check. Thank you. Skewness. So okay. Okay. So it measures the symmetricity of the distribution. Excuse me, I think someone has forgotten to mute himself. Please mute. Is there anyone who has forgotten to mute himself? Please mute. Thank you. Okay, so we are discussing about skewness. Skewness measures the symmetricity of the distribution or of the data. Okay, so skewness measures the symmetricity of the distribution or the data, and it is mainly defined with the beta 1 coefficients actually. So beta 1 coefficients, which is also known as coefficient of skewness, is defined as like as mu3 square upon mu2 cube. It is the ratio between the third and second order central moment. Okay, so this is the beta 1 coefficients which gives the excuse me, is there anyone who has forgotten to mute himself or herself? Please mute yourself. It is like disturbing. Hello. Hello. Thank you. So measure the symmetricity of the distributions, and it is like the coefficient of skewness is given by beta 1 coefficients, which is mu3 square upon mu2 cube. The value of the beta 1 identify whether the distribution is positively skewed, negatively skewed, or symmetric. And this can be verified with the help of the plots even. Suppose we have this kind of plot, or we have this kind of plot, or we have this kind of plot. Okay, so in the first plot, we can see in the first plot we can see like the most of the data lie within the first half actually. So this kind of like curve is called positively skewed actually. Then the second one, the major part of the data or the major part of the probability distribution is lie within the second half actually. So this is called negatively skewed. And in this one, actually 50-50, like it is exactly symmetric. So it is called symmetric distribution. So we have three kinds of skewness actually, like either the distribution is skewed, or that is the data is skewed, or the data is symmetric. So if the data is symmetric, this type of curve is like observed. But in case the data is skewed, then we have two possibility, either positively skewed or negatively skewed. Although there is many further subdivisions like highly positively skewed, extremely positively skewed, similarly highly negatively skewed, slightly negatively skewed, etc. Okay. So the basic concept is the most of the probability is distributed within the first half or within the second half. Okay. So this is the value. Again, we can see that for positively skewed data, actually the mean, the mean value is greater than median and is greater than mode. Usually this relationship can be observed for the positively skewed data. For the negatively skewed data, we can observe like the mean is less than median and which is less than mode. Okay. And for the symmetric data, actually, mean equal to median, which is also equal to mode. The people have already discussed know about the normal distribution. Okay. So in normal distribution, we found out that mean, median, and mode are equal because the distribution is symmetrical in nature. Okay. And most of the distribution that we will study in future are either positively skewed or slightly positively skewed. Very, not very, but there are less proportion of negatively skewed distribution as compared to positively skewed distribution. Okay. So is there anyone who have any doubt up to this point? Okay. So again, we can also have like if beta 1 is greater than 0, less than 0, or equal to 0 wala, I like concept. So again, the greater than 0, then it is positively skewed. Less than 0, that is negatively skewed. Equal to 0, this implies symmetrical in nature. Okay. So this is the how the curve is like differentiated or categorized with the help of skewness. Up to this point, is it okay? Can anyone confirm? Because I'm not able to like see the chats and I have no idea whether I'm audible or not. So please, anyone confirm once. Is there anyone?
Yes, sir.
Okay, thank you. So now the kurtosis section. So again, the kurtosis is defined as it measures like the kurtosis measures the flatness or peakedness. Kurtosis measures the flatness or peakedness of the distribution. Again, this can be visualized with the help of a curve or a graph. Suppose this is a curve. There is a one curve. There is second curve. There is third curve. Okay, just a graphical representation. Okay, so here the first curve or the peaked one, the peaked curve is called the leptokurtic curve. The middle one, which is neither highly peaked nor highly flat, is called mesokurtic. And the flat one usually is known as platykurtic. So on the basis of kurtosis, we have three kinds of curve: the leptokurtic one, which is the peaked one; the platykurtic one, which is the flat one; and there is the mesokurtic curve, which is also called normal curve because it is neither much flat nor much peaked. Okay. And the coefficient of kurtosis is like beta 2, which is defined as like mu4 upon mu2 square minus 3. Okay. Somewhere you can read like beta 2 is equal to mu4 upon mu2 square, and gamma 2, the corresponding another coefficient for kurtosis is, which is beta 2 minus 3. So this is the case, okay? So beta 2 is like this. Again, we have beta 2 either greater than 0 or less than 0 or equal to 0. Okay. So if it is greater than 0, then it is leptokurtic in nature. If it is less than 0, then it is platykurtic in nature. And it is 0, then we say that it is mesokurtic or normal. Okay. So these are the skewness and kurtosis coefficients. Now the next topic is like moment generating function. So the next topic is our moment generating function. Which is in short, we usually called it MGF. Okay. It is a simple formula actually. Moment generating function is defined as like it is denoted by MXT and is defined as expected value of e to the power tx. Okay. So this is the again a kind of moment, or we can say again it is expected value that is a kind of average, not the simple average that we are usually deal with. It is a kind of average which is e to the power tx. Okay. In a similar manner, like when we actually this is sorry, actually this is called moment generating function because it generates. We can say we are able to find out, estimate the moments. How we can estimate the moments? We can estimate the moment by differentiating this mxt, the moment generating function, and how it is defined as like d dt. Suppose kth order, we need kth order moment, then we differentiate the moment generating function to the kth order and put the value of t equal to 0, then we will find the kth order non-central moment. The kth order non-central moment. Okay, so this is the case. Then we have the similar kind of function, that is characteristics function actually. Characteristic function. And how it is defined? CF. Okay. It is defined as like phi xt. The similar one, the mxt, the phi xt, the expected value of e to the power tx. The similar one, the expected value of e to the power tx is moment generating function, and expected value of e to the power itx, the iota value, the imaginary representation of numbers, itx is called characteristic function. Okay. Now we have one inequality actually, which is very famous. And the thing is, it is Chebyshev's inequality. Up to this point, is there any problem with anyone? Anyone have any problem up to this point?
Yeah. E to the power of ITX. What is this I here? Imaginary
I
number.
here is imaginary. Yes, yes. The complex analysis that we have
Okay.
learned in complex.
Yeah, yeah. Okay.
Yes. So, okay. Thank
You
you.
have two components, then real component and again imaginary.
Yes. So this is the case. And just give me a moment. Okay. Now the next is Chebyshev's inequality. See, we use inequality when we have some information, not the full information, then we use some inequality actually. Okay. So this inequality is like bounds. Okay. So it gives bounds. And since we are dealing with probability, like probability, we are discussing about the probability, we have a probability bound. So it was given by Chebyshev's inequality. When and how it is like given? So suppose we do not have the information about the like distribution, but we have some information. And which kind of information? Like we have the average value and the variability. That is, we have the mean value and the variance of a data, but we do not have any idea about the distribution. Then we can set a bound for the probability. And the probability bound is like given this. The probability value of modulus value of x minus mu is the mean value, is less than k times of sigma. Sigma is the standard deviation, which is nothing but the under root of variance. Okay. So k sigma, this was is I always greater than or equal to 1 minus 1 upon k square. Or the similar approach, we can use probability that modulus value of x minus mu is greater than k times of sigma is less than or equal to 1 upon k square. Okay, so this gives the either maximum or minimum bounds for random variable. Okay, sorry, for the probability when we do not have the information about the distribution, but only the mean and variance of the distribution. There is also Markov inequality is there. We will discuss in later class actually that. There only we have the mean value, the only expected value is known. When we do not have known about have the information about the variability, then the Markov inequality is there. But when we have mean and variance, then we have Chebyshev's inequality. Okay. So now from there onward, we will discuss about some well-known discrete distributions. Okay, and then we will solve some numericals based on those distributions. So the first one is like suppose the first is discrete distribution. We will discuss about discrete distributions actually here. So the first one is like uniform. So usually when we are discussing that we have chosen a random number from 0 to 1, then we are discussing about uniform distribution, but in continuous case. Here, the uniform distribution for discrete case. Like when we roll a die, when we toss a coin, there we have a uniform distribution actually. And the probability mass function for the discrete distribution is called PMF, like is represented by probability that capital X is equal to small x. The capital X is the random variable and the small x is the value of that random variable. This is the standard notation to denote the PMF, probability mass function. For the uniform distribution, the PMF is given as 1 by n. When the x takes the value 1, 2, 3 up to n. Okay, so this is the probability mass function. For the uniform distribution, this is the discrete uniform. Okay, the expected value is like what? N, let me write in capital, n plus 1 by 2 n. This is nothing but n plus 1 by 2. This is the average value for the discrete uniform distribution. And then obviously the variance is also there. The variance of x, that is Vx, is defined as nothing but n square minus 1 upon 12. So this is well known actually. You can calculate the mean value and the variance value with the help of the moments formula that we have already discussed in above slides. Okay. So this is the case for a discrete case. The second one, which is the very famous, and I hope everyone have already at least heard, if you are not like learn this, the binomial distribution. Now, the binomial distribution is like in binomial distributions, we have a dichotomous nature. We have a variable which is dichotomous in nature. And what is the meaning of dichotomous? Dichotomous nature okay. So dichotomous nature means it has only two possibility, that is either failure or success, yes or no, true or false. When we are discussing or dealing about these kind of variables, then it is a dichotomous in nature. Okay, so it has only two nature. So this kind of problem can be dealt with binomial distribution. Suppose x is a random variable which is binomially distributed random variable. It can be represented as like b or bin with its two parameter n and p. Here the n is the number of trials and p is the probability of success. Okay, and these are the parameters. N and p are the parameters. And parameters is nothing but function of population values. Okay, like parameter, like population mean, population median, population variance. These kind of functional form of population values are called parameters. Okay. Now, when x is binomially distributed random variable, then the expected value of x, that is the mean value for that random variable, is n into p, is defined as the product of the parameter np. The variability is defined as, that is the variance or called variability. The variance is defined as the np1 minus p. Okay, sorry, let me first write the PMF of the distribution here. Okay, so the first one is the probability mass function for the binomial distribution is, it's n x p to the power x 1 minus p to the power n minus x, where x take value 0, 1 up to n, p takes value 0 to 1. Okay, so this is the the PMF of the binomial distribution. When you calculate the mean and variance, you will find NP as the expected value of the binomial variate, and the variance is NP1 minus P. Okay. Also, if you will solve, you will find out that the beta 1 coefficient, which is the coefficient of skewness actually. Okay, which is the coefficient of skewness actually. And this coefficient of skewness is like mu3 square upon mu2 cube. And you will find out it is 1 minus 2p divided by np cube. Q is nothing but 1 minus p actually. Okay. Q is 1 minus p here. Okay. npq to the power 1 by 2. Now you can see if we take beta 1 is either greater than 0 or less than 0, okay, or equal to 0 even, when p is, it comes out to be less than 0, okay, when p, like beta 1 is greater than 0, when p is less than half actually. And when p is less than half and beta 1 is greater than 0, it is nothing but negatively skewed. If you have remembered in the above slide, it's negatively skewed. Okay. Similarly, when beta 1 is less than 0, it happens only if probability of success is greater than half and the distribution is positively skewed. And when the probability of success equal to half it is 0, it is mesocotic, sorry, not mesocotic, symmetrical in nature. Okay, so these are like you can observe uh, when you you can observe with the value of the parameter p only. Okay, so that means binomial distribution can fit positively, negatively, as well as symmetrical distribution. Okay, now the next is its skewness, its kurtosis. Again, if you want, you can find out 1 minus 6 PQ divided by NPQ. Okay, again, the value of P and Q. With the help of the value of P and Q, you are able to find out whether the distribution is either like mesocortic in nature or leptocortic in nature or platycortic in nature. Okay, so also the MXT is also there. The moment generating function for the binomial distribution is Q plus P e to the power T whole to the power N. Okay, so this is the binomial distribution, the mean value, the variance value, the skewness, the kurtosis, and the moment generating function. Okay, we will solve the these quantity for all the different kind of distributions actually. Okay, is there anyone who want to say anything? Okay, if anyone have any doubt, please ask. Okay, so similarly we can evaluate the different quantities for different distribution. So let me write in brief, like for geometric distribution. For geometric distribution, uh, we will discuss when we need the first success. Okay, we will use the geometric distribution when we will perform an experiment kind of thing where we need the first success after a successive number of trials. Okay, so the PMF, the probability mass function for the geometric distribution is like q to the power x minus 1 into p when x equals 1, 2, 3, and so on. Okay, the expected value for the geometric distribution is q by p, and the variance is q by p square. You can find out the other quantities by yourself. It is already discussed by sir actually. Okay. Also, there is one point to remember. Okay. Geometric distribution has two form actually. The first one is like q to the power x minus 1 into p. And the second one is also there actually. Okay. Let me write here. The probability that x equal to q to the power x into p. And here x take value from 0 actually. And there is slight change in the expected value of x, which is nothing but 1 by p. Not x q by p, it's 1 by p. And the variability is same, I think, q by p square. Okay, so please be always be careful while using the form of for the geometric distribution. Either use q to the power x minus 1 into p or q to the power x into p. It's up to you. Okay. Then we have actually we have a memoryless property. Okay. We have a memoryless property, and in this property the actual theme is the initial time to get success. Like let me write the property first. Okay. The memoryless property is like the probability that x is greater than m plus n given the condition x is greater than n is equal to probability that x is greater than m. Okay, so what does it mean? It means that the initial time to get success, like the initial time to get success and the additional time to get success, and the additional time to get success have the same probability distribution. So the initial time to get success and the additional time to get success have the same probability of distribution. This is the property governed by very few kind of random variable, and the one is a geometric random variable, and it is memoryless property. Okay. Now again,
That means, are you saying
yes,
first time to get success, the probability
yes,
will be same as the probability to get second time success also after getting first time success?
yes. The waiting time is there actually, no? The waiting time, the distribution for the waiting time and the distribution for like the x. Suppose the probability value that x is greater than m plus n. Okay, the greater than m plus n. It's a number actually, m and n. Suppose 2 and 3. 2 is weak and 3 is weak. So m plus n, 2 plus 3, 5. Probability that x is greater than 5. Okay, given x is already past n, that is 2. It is equal to probability that x is greater than 3. So that means the probability of waiting time in that is additional time or waiting time and initial time have the same probability distribution. I think Dhananjay ji, you have some question. Let me. Okay. Yes, Dhananjay ji, if you have any doubt, you may ask here. Which function is used in memoryless function? Okay. Which function? Actually, there is no function. No? Here, the x follows the geometric distribution. This is the PDF. I am discussing about the geometric distribution. Okay. Here, x is a random variable which follows the geometric distribution. That means it follows this form q to the power x minus 1 into p or q to the power x into p. Okay. And suppose I need to find out whether the probability that x is greater than 8. Let me write here. Just let me write something. I am saying probability that x is equal to 8. Okay. When x follows the geometric distribution, given x is greater than 3, I am going to solve this question. Okay. I need to find the probability for this question. Since I already have some information that x is already greater than 3, so this implies with the help of the memoryless property is equivalent to probability that x is greater than 5, because 8 can be written as 5 plus 3. This is the memoryless property, but this property only holds in the geometric distribution here. In discrete case, the geometric distribution, and in continuous, we will discuss again for the exponential distribution. Okay. Is there any doubt again? But sir, assignment question, memoryless function are asked. Memoryless function, that means it is discussed about, suppose here, just see, you have your answer actually in your question. You are asking about memoryless function. Okay. What is this? If you find out, you will find it is a function. Na? So q to the power x minus 1 into p is a function. It is a special kind of function which we termed as probability mass function, but also it is a function. So yes, it is either geometric distribution or geometric function, or it is a exponential distribution or exponential function. Okay, but the specific term is the distribution because we are dealing with the special kind of function. Okay, that follows some properties, and those properties are like or valid for PDF or CDF. Okay, okay, okay. Any other doubt? Okay, then we will just go one or two more distribution and then we will solve some numericals actually. So there is one more distribution, that is negative binomial. Okay, so again, like we have discussed about binomial distribution, and uh, this is negative binomial distribution. Okay, so in negative binomial distribution, it is kind of inverse or the opposite of the binomial distribution. And in which or in what terms it is opposite? Suppose in binomial distribution, is there any doubt? Uh, it's Raja Sulochana. I think you want to ask anything. If yes, you may type. Okay. In binomial distribution, okay, we have like number of trials is fixed. Actually, we have fixed number of trials and number of success is random variable. Okay, but in case of negative binomial distribution, it reverse. Okay, so that means we have fixed number of success or number of failure, whatever you use, you will take you use terms, and the number of trial is a random variable, and the number of trials are random variable. So in this context, we say that the negative binomial is inverse or negative or reciprocal of the binomial distribution. Okay, and yes, its CDF, sorry, its PDF is also very simple. Okay, you may like the PMF is probability that x is equal to x is defined as x plus r minus 1 p r minus 1 p to the power r cube, that is 1 minus p to the power x. Okay, here x is the number of like failures, number of trials actually, sorry, number of failures, sorry, yes, number of failures is x, and r is number of success, and the total number of trial is number of failure plus number of success, that is x plus r. Okay, so this is our total number of trials. You may use different forms of this negative binomial actually, that's why I am specifying here x. I have considered x as number of failure, r as number of success, then total number of trials are x plus r, which is number of success plus number of failure. Okay, and again the expected value of x for when x follows a negative binomial is like r p and by sorry r q by p, sorry, r q by p, and the variance of x is like r q by p square. Here the r and x, sorry, r and p are the negative binomial, r and p are the parameters. Okay, these are already discussed in detail in lecture actually. I'm just trying to write, and the last distribution. Okay, let me write the last distribution, and this one is like hypergeometric distribution. This one is like hypergeometric distribution, and this hypergeometric distribution is see, again we have some one more notes. Okay, in binomial distribution we are discussing about when we deal with replacement. Okay, when our random experiments are performed under with replacement case. Okay, and in hypergeometry, we perform the experiment or the trial under without replacement case. Okay, so you may say that both are similar, but the experiment, the conduct when we conduct the experiment under hypergeometric case or under binomial case, then we are just saying either we use the without replacement case or with replacement case respectively. Okay, the PMF for the hypergeometric distribution is like M C X n minus M C n minus X and N C n. Here n is like here n is the total number of trials, okay, and m is the favorable number of trials, and out of these we select small n number of quantities or sample. Okay, so this is the three parameter, and this is the PMF for the hypergeometric distribution. Again, for that case, expected value of x is small n, m by n, and the variance of the random variable for the hypergeometric case is n, m by n, n minus m divided by n, and it's capital N minus small n upon capital N minus 1. So this is the case for like variance. If you just wanted to observe something, you may find M is the favorable case, capital M is the favorable case, and capital N is the total case. So this is a kind of proportion in favor of the favorable case. This is N, this is P, N minus M, this is Q, and this is the case, the terms or the constant for the without and with, for which connect the without replacement case and the with replacement case. Okay, so this is just similar to the binomial distribution, but under without replacement consideration. Okay, so these are the some distributions. Okay, so up to this point, if anyone have any doubt, he or she may ask. Otherwise, we will solve some numericals on the basis of these topics. Is there any question? No. Okay, then let me write a question and then we will try to solve. Here the first question is, a point is chosen at random. A point is chosen at random on the circumference of a circle on the circumference of a circle of radius 1 with center at the origin, with center at the origin. Okay, that is the polar angle x, that is the polar angle x of the point chosen has uniform distribution on the interval 0 to 2 pi. Okay, this is the information given in the question. Now the question is, determine the standard deviation standard deviation of the random variable y, which is defined as 3 by pi times of x plus 2. Is it okay up to this point? The question. Okay, the question is like a point is chosen at random on a circumference of a circle of radius 1, okay, with center at the origin, that is the polar angle x of the point chosen has uniform distribution on the interval 0 to 2 pi, because there is a 360 angle which is 0 to 2 pi. Now determine the standard deviation of the random variable this. Okay, so let me start. Since this is a question of actually a kind of uniform, continuous uniform distribution actually. Okay, so let me write here for the continuous case first. See, this is not yet like given in the lecture, but let me write. Suppose x is a uniform 0 theta, for example, then the PDF is 1 by theta when x belongs to 0 to theta. Sorry, sir. Okay, I'm writing it correct actually. X belongs to 0 to theta. Okay, so this is the continuous uniform distribution. The same. Okay, so here for our case, it is given that x belongs to 0 to 2 pi. So in that case, 1 upon 2 pi minus 0, that is 1 upon 2 pi is the PDF. Okay, and the expected value in this case is b minus a. That's not expected. We need variance actually. The variance of x is b minus a whole square upon 12. Okay, here the value of b is 2 pi minus a is 0 upon 12. So the variance of x comes out to be like 4 pi square upon 12 comes out to be pi square upon 3. So this is the variance for the x random variable. Okay, this is the variance for the x random variable, and we are given the random variable y, which is associated with x via 3 by pi x plus 2. Okay, so variance of y, as we have already like see the property for this now, variance of y is equal to variance of 3 upon pi x plus 2, and since variance of ax plus b is a square variance of x, so variance of this is 3 upon pi square variance of x. Okay, so 3 upon pi square is 9 upon pi square into variance of x that we have already calculated, pi square upon 3. Okay, pi square is cancel out, 9 by 3 is cancel out. So variance of y equal to 3. And we need to calculate the standard deviation of the variable this. So the standard deviation of the variable y is under root of variance of y. So the standard deviation of the variable y is under root of 3. So this is our final answer. 4 pi, okay, Dhananjay ji, you have told me 4 pi, and what is the, where is the 4 pi is there? Can you please explain? And what you want to ask? Okay, okay, no problem. You may actually unmute yourself and tell me if you have any doubt. Okay. Okay, now the next question is like, okay, If anyone have any doubt, please ask. Okay. A motorist encounters, let me write the question first. A motorist encounters consecutive traffic lights. Consecutive traffic lights, each likely to be red. Each likely to be red with probability 0.2 and green with probability 0.8. What is the probability that, now the question is, what is the probability that the number of green lights passed by the motorist before stopped first time. Before stopped first time by a red light is 4. Red light is 4. Okay, see the question. A motorist encounters consecutive traffic lights, okay, and each likely to be red with probability 0.2 and green light probability 0.8. Simple question, okay. We are traveling and the probability that we will encounter a red light with 20% chances and green light with 80% chances, okay. Sorry, I am leave system. Okay, sorry Dhananjay, but is it not possible to change the timing? Okay, it is already defined. So you may see the recording. Okay, you may see the recorded lecture on the YouTube channel. Okay, so the thing is, this is a very logical question. Okay, and what is the question actually? The question is, what is the probability that the number of green light passed by the motorist before stop the first red light is 4? Okay, the first, that means overall, we need the first success. And what is the success is? To getting a red light. Okay, so it's very simple question. So we have, can anyone tell me which distribution we are going to use here to solve this problem?
Geometric distribution.
Geometric, exactly.
Geometric distribution.
Yes, because as we have told, like we have seen in the previous, the geometric distribution is used when we are dealing with the first success. And before the first success, how many number of failures are there? 4. In this question, 4. So here, suppose X follows geometric distribution with the probability of success P. And what is the probability of success here? To getting a red light. And the probability of getting a red light is, right, 0.2. So it's 0.2. Now we have the distribution form, the probability that x equal to q to the power x minus 1 into p, or x equals 1, 2, and so on. Okay, we are given some values. The value of x here, probability that x is equal to, in this form, in this PMF form, as you notice, x is the number of failure and p is the number of the first success before the number of failure. So what we need the value of x is 4 here. The probability that x is equal to 4 equal to, what is q here? Q obviously 1 minus 0.2, that is 0.8. 0.8 to the power 4 minus 1, 0.2. Obviously 0.8 to the power 3, 0.2. Now you can solve this via like calculator. So you may write 0.2 to the power 9, 0.2 or 0.2 to the power 10. It comes out to be 0.1024. It's a very famous number. If anyone know 1024, anyone have any idea what is 1024? Okay, so this is the final answer actually. Around 10% chances that the person, look, in the previous class, I told that always try to interpret the result as well. Okay, here we find that 10, around 10%, let me say around 10%. So it is a 10% chances that the motorist will stop at the first red light at after the 4 green light. Okay, that means
Sir,
after the,
here
yes,
it is actually your 0.8 to the power of 3. You come down this one, no?
yes,
Is
yes.
not 0.2 to the power of 9, no? Because
Okay.
here, if you see zero point 0.2 cube is point not 8 point cube.
Okay.
Okay.
Got it. I think
Yeah,
it's
this
yes.
is not
Thank
correct.
you.
Yeah, the last line that
This
equal
line is actually not correct, you know.
not correct.
This
Yeah,
one.
there
Yes.
only it is not.
Thank you. Actually, 0.8 to the power 3 comes out to be like what it comes out to be 864, and it's how much it comes?
512. Point five
Yes,
one
yes.
two.
0.512. Okay, thank you. Yes, this one is okay, correct now. I'm just confused and write it like this way. Okay. So again, this one is also not the correct one. Okay, thank
Okay.
you. Okay. So the probability is like this. Okay. And the interpretation is like the same question. What is the probability that the number of green light passed by the motorist before stop at the first red light is 4 is 10% of the time this will.
Yeah, the answer is correct. What you have put is correct finally.
Okay.
Point
I'm
one
just
zero.
seeing, yes, I have just seen 1024 and since point 8
No.
is there,
And
so
this is
just
correct. What you have put finally is correct. That
yeah.
point 1024 is correct.
Okay.
Even
Okay
if we
then.
might, yeah,
Yes.
2 to the power of
Okay.
10, that, yeah.
Is that is not correct actually. Yes. Now the next question is a very basic question with the property of the PMF actually. Then the question is, let X be a discrete random variable. Okay. Let X be a discrete random variable having the PMF, having the probability mass function PMF given by, the PMF is given by like this. It's minus 2c by n when n equal to minus 2 and minus 1. It's d when n equal to 0, and it's cn when n equal to 1 and 2. Okay, so this is the PMF for the random variable x. Now, where c and d are obviously a positive number is there, where c and d are, where c and d are positive real number, and we have also one more condition. The probability that modulus value of x is less than 1 equals 3 by 4. We need to find the value of c and d. Find c and d. Okay. So can anyone tell me how to proceed? Let's see. We are given the PMF and we need to find the value of c and d. We have two variables. So we need two equations kind of thing actually. Okay. So the first equation, how can we, like the first equation is probability that x modulus x is less than 1 equals 3 by 4. This is okay. How to construct the second equation? Can anyone tell me? See, we have the property of the probability mass function that the summation over the range of x comes out to be 1. Okay. And here the value of x here is n, actually small n. The value of n, the possible values of n is -2, -1, 0, and 1 and 2 with the corresponding probability as. So obviously, with the help of this probability, we have like -2c by n, -2c by n, when n equal to -1 and -2, plus d when n equal to 0, plus cn when n equal to 1. Cn when n equal to 1 and 2. This comes out to be 1. Okay. So just put -2c upon -2 plus -2c upon -1 plus, yes, any question, plus d plus c cross 1 plus c cross 2 equals 1. Okay. So yes, it's c, it's 2c, it's d, it's c, it's 2c equals 1. It comes out to be 6c plus d equals 1. So we have a equation 1, which is a two variable linear equation. Now we have second equation. Probability that modulus value of x is less than 1 equals 3 by 4. Also, probability that modulus value of x is less than 1 equal to, it's a 3 by 4, 1 by 4, 3 by 4. 3 by 4. Okay. So yes, modulus value of x less than 1. Okay, not equal to, it's less than 1. So overall, there is only one value of n that satisfies those condition is n equal to 0. And the probability that n equal to 0 is d. So it's directly we can write probability that x equal to 0, which is equal to 3 by 4, which is d equal to 3 by 4. So we have the value of d equal to 3 by 4. Putting the value of d in equation 1. So put d equal to 3 by 4 in equation 1. We get 6c plus d equal to 1. 6c plus d, which is equal to 3 by 4 equal to 1. From here, 6 equal to 1 minus 3 by 4. From here, 6 equal to 1 by 4. Simple. From here, it's 1 upon 24. So we have c and d, which is equal to 1 upon 24, and its d is 3 by 2. Is it okay up to this point? Any doubt? Okay, the next question. Again, the next question is like the similar one. So let me. Okay, I have a simple question. Okay, a certain airline company, observes that a certain airline company observes that 5% of the persons 5% of the persons booking tickets on a flight do not show up for the flight. So it sells 51 seats on a plane, 51 seats on a plane that has 50 seats. Okay, simple question. Okay, since they observe that 5% of the person booking tickets do not show up on the flight. So instead of selling of 50 seats, 50 tickets for the 50 capacity seats, he sent 51 seats. He sold sell 51 seats. Okay. Then what is the probability that there will be a seat available? There will be a seat available for every person who shows up for the flight. Who shows up for the flight. Is it okay? The question is clear. The capacity of the airline or the flight is 50, and since they observed that 5% of the person do not show up for the flight, so instead of selling the 50 seats, they sold 51 seats. So what is the probability that there will be a seat available for every person who shows up for the flight? Simple question. So can anyone tell me how to proceed? Is there anyone who can let me know? Here, obviously, X is the number of persons showing up for the flight. Number of persons. X, we define the random variable X as the number of persons showing up for the flight. Okay. So here X, actually the random variable X follows the binomial distribution actually with the probability of success of what? Since we will discuss about showing up and 5% of the people not showing up, that means 95% of the people will show during the flight. So that means 0.95 is the probability of success when we are discussing about the person, the probability of person showing up for the flight. Okay. And what is the number of trials? So here the number of trials is 51. Okay. Because instead of selling 50 seats, the airline sold 51 seats. So it is a simple binomial distribution problem with the parameter n equal to 51 and the probability of success is 95% or 0.95. Now, what is the question? The question is probability that there will be a seat. There will be a seat available for every person. So that means what? So that means the probability, since the capacity, the flight capacity has 50 only. Okay. So this implies the probability that everyone will get a seat is only possible if the number of persons, that is X, is either 50 or less than 50. So probability that X is less than or equal to 50 is our required probability. Is it okay up to this point? I think. Okay. So probability that X is less than this is 1 minus probability that X is greater than this. Simple. The use of complement. So it is 1 minus probability that X is 51 because there is a n. The value of X ranges from 0 to n and the value of n is 51. So this one. So now it's a simple calculation. 1 minus it's 51C51 0.95 which is p to the power x which is 51 0.05 which is 1 minus p to the power 51 minus 51. It's 1 minus something. It's very like 0.07. When you are solving these, actually, you'll find 0.0731 actually. So once you are solving the final answer, it's 0.9269. So probability that X is less than or equal to 50 is so 92.69% chance that every person who show up in the flight will definitely get the seat. This is the question. Is it okay up to this point? Okay. Let me write the next question. Now the next question is, let x be a random variable. Let x be a random variable having the Poisson distribution with parameter 4. Okay. And let E be an event. Let E be an event such that probability that the event E given xi, not xi, it's x actually, given x equal to I equal to 1 minus 3 to the power minus I, for I equal to obviously 0, 1, 2, and so on. We need to find the probability of E. Find probability of E. It's a simple question again. We have a straightforward question. We need to use some previous concept like multiplication rule here. The first thing is x follows the Poisson distribution. Okay. So x follows Poisson distribution with parameter 4. So the PMF for the Poisson distribution is what? E to the power minus lambda. If there is lambda parameter, then e to the power minus lambda, lambda to the power x upon x factorial for x equal to 0, 1, 2, and so on. This is the standard PDF of the Poisson distribution. We are given the parameter lambda equal to 4. So the probability that x is equal to e to the power minus 4, 4 to the power x upon x factorial. Okay. This is the formula, this is the PDF for parameter x equal to 4. Also, we know the law of total probability. Since law of total probability states that the probability of any event E is defined as the summation I from 0 to infinity probability that E given x equal to I, the conditional probability multiplied by the probability of the conditional event, that is probability that x is equal to I. So this is the case. Okay. We have like here, if you know, we are given x follows Poisson, and this one is already given here in question, 1 minus 3 to the power minus I. Okay. So just we need to find the probability of E. So let's use this formula only. So probability of E equals summation. Probability of this is like 1 minus 3 to the power minus I. And probability of x equal to E is like Poisson. So it's e to the power minus 4, 4 to the power I upon I factorial. Simple. Now we just need to simplify this. How to simplify this? So there is summation e to the power minus 4 is taken as common. We can write like this: e to the power minus 4 summation 4 to the power I upon I factorial. Then minus again e to the power minus 4 summation 4 by 3 to the power I upon I factorial. Okay, I'm just multiplying the term with the within the parenthesis term. Now, since if we know, since the summation from 0 to infinity x to the power I upon I comes out to be e to the power x actually. This is the formula. Okay, so you can see here what is this and what is this. So you may find e to the power minus 4 into e to the power 4 minus e to the power minus 4 into e to the power 4 by 3. Because here, instead of x, in place of x, it has 4. And in the second term, in place of x, it has 4 by 3. Okay, so this is the case. Now we need to just solve this. Nothing 1 minus e to the power minus. It's 12 minus 12 plus 4, it's minus 8 by 3. And if you use the calculator, the value of this is like 0.0695. And after solving, we will get probability of the event E equals 0.9305, which is our required probability of the event E. Okay, so this is the question and this is how to proceed with the solution. Any doubt up to this point? Okay, now I have one more question. Okay, a simple one. We are given the probability of a success. The probability of a success in a single trial is 0.05. The probability of success in a single trial is 0.05. Now the question is how many trials are needed? How many trials are needed? On the average, how many trials are needed to get the first success? Can anyone let me know how to solve this? Any idea, any hints, or anything? Anyone? Okay. See, again,
Simply, probability of
yes,
success you are saying is 0.05. Say 1 divided by 0.05, 20 times if you do, one success, but that
will
is
be
not
there.
correct. Yeah, geometric, you have to use geometric distribution.
Exactly. It's
That
a
way,
simple again, actually. Yes, you are right, actually. It's a geometric distribution again, because I am discussing about the like the first success. Okay, and I have given the probability of success as well. So here the P is given 0.05, and uh, I want to like calculate the average. Okay, on an average, in not about individual, in an aggregate form I'm discussing about. So in an on an average, 5% of the time it will get success. Okay, so obviously x follows geometric distribution with probability 0.05, that is 5%, and the expected value under this condition is 1 by p, that we have discussed in the above slide. Okay, so what is the value of x is 1 upon 0.05, comes out to be 20. So at least 20 trials will be there to get the first. Not at least, sorry. The wording is like on an average, 20 trial is there to get the first success. Okay, so hope this will clarify the answer. Okay, I have one more question actually, one interesting question actually. So it's somewhat long, but let's try to solve this question. See, the question has three concentric circles. So like we are given three concentric circles of radii 1 by root 3, 1 and root 3 meter. Okay, are drawn on a target board. On a target board. If a shot falls within the innermost circle, if the shot falls within the innermost circle, 3 points are scored. Okay. If it falls within the next two rings, if it falls within the next two rings, then the scores are respectively, then the scores are within the next two rings, then the scores are respectively 2, right here, 2 and 1. Okay. And the score is 0 if and the score is 0 if the shot falls outside the outermost circle. Okay. Now the question is, if the probability density function of the distance, if the probability density function PDF of the distance of the hit from the center of the target is, we are given the PDF 2 divided by pi 1 upon 1 plus r square for r is greater than or equal to 0. This is the PDF. Okay. Now find the expected value of the score. Find expected value of the score, that is expectation of r. Okay. It's a simple question actually. Just a long question. So let me question is like kind of this. Okay. So we have three concentric circle with three different radius. So we need to find when we fire a shot, the shot will fall within either the innermost or the rest two circles with the scores 3, 2, and 1 respectively. Okay, so obviously the score will be like assigned like this. So if the scores are like the scores 3, the first case. The second case is like if this 0 to 1 by 3, sorry, not this, it's 1. The scores are like 2. And the third case is, the question is, it's 1, it's root 3. The scores 1. And the fourth, if r is greater than root 3, the score is 0. Okay, so this is the case. Now we need to find the expected value. So first we need to find the probability, obviously the probability, because the, not probability, the expected value of r is what? Summation r into probability that r equal to r, and the r value is either 0, 0 to something, something to something, and all. Okay, let me write here. I'm not discussing about the discrete, I'm discussing about the continuous case. So this is the case. Now for the first circle actually. So we will start with the 1. But before that, let me first write the CDF actually, so that we can directly use the CDF form. So we are given the PDF is 2 by pi 1 upon 1 plus r square. This is the PDF. And we know that the integral of 1 upon 1 plus r square dr is what? Anyone?
Tan
Anyone?
inverse R. Tan inverse R.
Exactly, tan inverse r. So okay, so every time we are going to integrate this term, so we directly use the tan inverse r in place of this term. Okay, so obviously you know the property of the CDF, the probability that the x lie within A to B is FB minus cap CDF of FB minus FA, and here only you can use 2 upon pi, which is this quantity, 2 upon pi, and 1 upon 1 plus r square is like tan inverse r. So it's tan inverse B minus tan inverse A. Is it okay up to this point? Hope so. We can write like this. Now the next term is we use the value of A and B. So probability of 0 r, so 1 by root 3. It comes out to be 2 upon pi tan inverse 1 by root 3 minus tan inverse 0. So it comes out to be 2 upon pi. So it's pi by 6 minus 0. It comes out to be probability that, okay, see one thing, I can use less than or equal to or less than, both have the similar meaning if we are dealing with the continuous random variable. Okay, so if I use this or I'm not using this, that means in case of continuous random variable, both have the same meaning. Okay, so it comes out to be like 1 by 3. Similarly, the probability that it's 1 by root 3, so 1 comes out to be 2 by pi, again tan inverse 1 minus tan inverse 1 by root 3. Okay, so it's 2 by pi, so tan inverse it comes out to be pi by 4 minus tan inverse 1 by root 3 comes out to be pi by 6. Now the simple calculation is this. So the required probabilities after solving 1 by 6, it's a simple actually, just a calculation. We need to understand this concept only. Okay, the tan inverse one, because it is not quite frequent in our numericals. Okay, now again the term probability that it's 1 to root 3, it comes out to be, I'm directly solving this. Okay, I'm directly going to solve this. It comes out to be like it's okay, 1 to this to this. It's again comes out to be 1 by 6 actually when we will solve. Okay, so the first one is 1 by 3, the second one is 1 by 6, the third one is 1 by 6, and the last one have 1 by 3 probability if you are going to solve. Probability that greater than r is greater than root 3, it comes out to be 1 by 3 if you are going to solve in the similar manner. Okay, so we have probability actually, we have probability distribution. So it's if r lies between 0 to what this, I need to write the scores. No? So here the scores and here the probability. Okay, so scores are like 3, 2, 1, 0 with the corresponding probability like 1 by 3, 1 by 6, 1 by 6, 1 by 3. So the expected value of R is summation. Yeah, I think score, let me write here X for the simplicity purpose, or let's write the score directly because I'm not using any word, is no need to write this, write this. So it's 3 into 1 by 3, this multiplication, plus 2 into 1 by 6, plus 1 into 1 by 6, plus 0 into 1 by 3, comes out to be 1 plus 1 by 3 plus 1 by 6 plus 0, comes out to be 6 plus 2 plus 1 upon 6. So expected X score is 3 by 2. This is, so is it okay up to this point? Anyone? Is there anyone who have any doubt in this question? Then we can solve again or we can discuss again. If not, I think I have solved all the questions that I have written here actually. So if you have any question, any doubt, you may ask, or we can conclude our session here. Anyone? Okay. So everyone just see this. If you want the recording, already the NPTEL have provided you the link, but you can visit this YouTube link. From there, you can download the, you can see the lecture, recorded lecture, and you can see my site. From there, you will find out the all materials, all PDF and everything. Okay. So let me stop here. If you have no any doubt or question, let me first stop the recording.